All right, welcome back. We are going to be discussing or continuing on our discussion of Chapter 2 of Campbell's biology, again, delving into the chemical context of life. So, in this lesson, we are going to be looking at concept 2.2 that an element's properties depend on the structure of its atoms. Okay, so again, words that we need to define, right? So to start off with, each element consists of something unique called an atom. Okay? An atom is simply a smallest unit of an element. And how that atom looks is going to tell us how that element behaves and how it would respond in various chemical reactions. Okay? So let's keep going right here and go into atom a little bit more. Atoms are composed of subatomic particles. Okay, so atoms are in fact made up of smaller units. The thing is, though, those smaller units don't behave the same way as the actual atom of the element itself. Okay, so let's look at what some of those subatomic particles are. One is we have something called a neutron. Neutrons, as the word or the base of the word neutral would indicate, has no charge to it. Okay, no electrical charge. It is a big subatomic particle, so it has mass, but it has no charge. We also have something called a proton, which does have a charge. It's similar in size to a neutron, but it in fact has a positive charge associated with it. We also have electrons, and electrons have a negative charge associated with it. Okay? Now, when I say positive and negative, this is very much related to the positive and negative ends on magnets. Okay? And as I'm sure you've discovered, if you try and stick the negative end of one magnet up against a negative end of another magnet, they repel each other. Okay, but the negative end of one magnet will stick to the positive pole of another magnet. Okay, so these positive and negatives act in a very similar way, and that negatives, like charge, repels each other. So two negatives would push each other apart, but negatives are attracted towards positive particles. All right, so let's put these atomic particles into a structure. Okay, here's a couple different ways of representing it. Okay, and they have a lot of similarities in how we're representing. So first of all, we have the neutrons and the protons clustered together here in the center, and that center is called the nucleus. Okay? Now, you might ask, well, why aren't these positive particles pushing themselves apart? Well, in fact, they are, but there's another force holding them together, and that force is way above our pay grade right now. Okay? So we're not going to delve into what that force is. You will get to it later in chemistry. Okay? Now, this is in the center and forms a little cluster. The electrons kind of float around the outside, or you could say orbit around the outside, in kind of a similar way that the moon is orbiting the Earth or the Earth is orbiting the sun. Now, unlike the moon or the Earth, these aren't actually just going in a circle, but they are actually living in a sphere that surrounds this nucleus. So you can imagine that maybe the nucleus is the yellow yolk of an egg, and the electrons are on the surface on the shell. And this right here, what we're looking at, is a cross section. Okay? So the electrons could be a similar distance away from the nucleus all around this three-dimensional surface. Okay. So this is a very simplistic way of representing it. Another way of representing it is that these electrons exist in a cloud that surrounds the nucleus. Okay. Now, both of these are models that help us understand the way atoms behave, but it isn't necessarily completely how they look. We have a very hard time seeing things this small, so oftentimes what we see is a representation of the result of how things are built up. Okay? So, although both of these representations have truths to it, don't lock this into your head as the only way it exists. Okay, this is just simply a model that helps us understand how these atoms work. Okay. Now, we have certain number of protons, certain number of neutrons, certain number of electrons. Okay. The differences there is what gives us these different elements. Okay. And so I need to explain some different numbers associated with these elements in order for you to get a grasp on it. Okay, number one, we have the element itself, which has a symbol associated with it. This is a 1 to 2 letter abbreviation of that element. So this is the element helium. We abbreviate it by the letters He. Okay. Others, such as oxygen, just simply has a single letter. In the case of oxygen, that is a capital O. In this circumstance, when we're talking about elemental symbols, the first character is always capital. If it has a second character, it is always lowercase. Okay. One number associated is the atomic number of this element. Okay. This is the number of protons in the nucleus, and this is something that never changes for that element. So helium will always have an atomic number of 2. Hydrogen will always have an atomic number of 1, and so forth. Okay? Another number associated with this is the mass number. Here, one way of representing an element is to have its symbol with various numbers associated with it as a superscript or subscript. Okay, and in this case, the atomic number, or the number of protons, is in the subscript. The mass number is in the superscript. The mass number represents the sum of protons plus neutrons. Okay, so if we know we have 2 protons, and we know that this number here is the number of neutrons plus protons, we know that we have 2 protons and 2 neutrons, which gives a mass number of 4. Okay. Another number associated here is something called the atomic mass. Okay. The atomic mass is the actual measurement of how much an individual atom weighs. Okay? This is measured in units called daltons. Don't be too disturbed by that or focus too much on this, but as an approximation, both neutrons and protons have about a mass of 1, and electrons have almost a mass of 0, okay? But not exactly. Electrons do, in fact, have a little bit of a mass, and neutrons are a little bit heavier than protons, okay? The only thing we really need to concern ourselves with in terms of atomic mass is if we are trying to get a specific ratio of one element to another element, we have to utilize its atomic mass in order to weigh out that material. Okay, and I will leave that to chemistry to explain all the ins and outs of that. So don't get too hung up on that. Just recognize that the atomic number is the number of protons in the nucleus, and the various mass numbers kind of represent the amount of protons plus neutrons. Now, all atoms of an element have the same number of protons, but they can actually vary in the number of neutrons. Okay? When we have an element that has different numbers of neutrons, we refer to those different versions as isotopes. So here's an example of carbon. We have carbon 12, which has 6 protons and 6 neutrons. We have carbon 13, which has, again, 6 protons, doesn't change, but now has 7 neutrons. Over here we have carbon 14, which has 6 protons and 8 neutrons. Again, protons don't change. Number of neutrons do change. Okay? I'm not going to harp on this too much. Just recognize that this is what the word isotope is referring to. All 3 of these carbons would behave exactly the same way in a chemical reaction. The thing that is different, however, is like a person riding a bicycle. When you get more and more neutrons present, it can be a little unstable. Okay? And when it's a little unstable, it's likely that one of those neutrons, or maybe 2 of those neutrons, might pop out and turn carbon 14 back into carbon 12. Okay? Way of thinking about this is imagine riding a bike. Okay? One person riding a bike, not a big deal. If you have 2 people riding a bike, a little bit more precarious, but pretty easy to accomplish. Okay? If you start loading people onto a bike and you attempt to go on a long ride, sooner or later, one of these guys is going to fall off. And when that person falls off, they are a large object flying through space, and they could hit something and cause damage. Imagine driving past one of these little vendor booths here, a person falls off, knocks over the table, knocks the display down, all that stuff, okay? So, these things that spontaneously decay, or is because they are unstable, and the things that come off of it can cause damage, okay? So when we talk about radioactive elements, or isotopes of those elements that are radioactive, they do, over time, leach off both particles and energy, and that can cause damage. Now, we can utilize that to our benefit in that one of the things that are given off is X-rays, okay? So consequently, we can make a dye that is utilizing radioactive isotopes. We can put that dye into something that is readily taken up by things such as cancerous cells. We can then take an X-ray image of you and we can see, oh, look, all of the cancer is right there because the cancer sucks up the radioactive element, and the radioactive element is giving off X-rays, so now we can see it. Okay? We can also utilize this principle to date things. Okay? I am eating and breathing, so consequently I am constantly taking in more and more carbon, and so I have a certain ratio of carbon 14 to carbon 12. Okay? When I die, I cease taking in new material. So I slowly over time, the amount of carbon 14 in my body will slowly start to disappear. Okay? This breaking down of the upper isotope into the lower isotopes happens at a defined rate called a half-life, and we can use this to date how old something is. Okay? And we will pick up this concept in part 2 of this lecture.